Awesome. So welcome back. The title of today's lecture is Encrypted Computation. So let's do a quick recap of the things we've discussed so far in this lecture. So we've seen that virtual black box obfuscation is essentially the strongest notion of obfuscation we could wish for. It hides everything but the input-output behavior of a program in a black box sense. Program that's VBB obfuscated doesn't give you more than black box access to this program gives you. We have seen that VBB obfuscation is possible for programs that compute learnable functions. So if whatever the program computes in some sense cannot be nicely hidden anyway because it's learnable, then we can also obfuscate it. Furthermore, and more importantly, we've seen that VBB obfuscation is impossible for a quite large class of programs. It was, if you recall, these programs that can kind of detect programs that do the same thing as they themselves do. Also, we've seen that the notion of indistinguishability obfuscation, or IO, provides a somewhat weaker but apparently still meaningful guarantee for obfuscation. Still, as we've seen in the last lecture, indistinguishability obfuscation is actually the best kind of obfuscation that we can hope to achieve. So even if there is a fantastic unbounded obfuscator that turns a program into something that leaks a minimum amount of information through its source code, then an indistinguishability obfuscator is as good. All right, so what we're going to discuss today is one of the central tools that is used in the construction and study of obfuscation schemes, namely homomorphic encryption. I have briefly alluded already a little bit to homomorphic encryption in the first lecture, but today we're going to take a deep dive into this topic. And a high-level reminder maybe before we go into the details, homomorphic encryption allows us to perform computations on encrypted data without decrypting or the need for a secret key. So it allows you to blindly perform computations on encrypted data. All right, so let's first talk about the syntax of fully homomorphic encryption. So in a way, this is first a normal public key encryption scheme. We have a keygen algorithm which produces pairs of public and secret keys. We have an encryption algorithm which takes a public key and a message M. Just say that the message M is a bit for now and outputs a ciphertext C. Then, of course, we have a decryption algorithm which takes the secret key and a ciphertext C and outputs a message M. Now, the new thing, the fourth algorithm that we have now is a public evaluation algorithm. This evaluation algorithm only takes the public key, a circuit C, and a bunch of ciphertexts C1 to Cn, and outputs a ciphertext C prime. So that's just the syntax. Apart from this evaluation algorithm, I haven't really said what it's supposed to do. We're going to do this on this slide. What do we require from FHE schemes? The standard thing is correctness. And correctness we first define as for standard public key encryption schemes. Namely, if I encrypt a message M under public key PK and then decrypt it, I will get the same message M. So encryption and decryption are decryption is an inverse operation to encryption. I can recover my encrypted message M from a ciphertext. Next thing is in CPA security or chosen plaintext security, and that's really the same as for standard public key encryption. So when we encrypt bits, I give my adversary, let's see, let's maybe draw this just as a quick reminder. We have an adversary A here, and I'm choosing a random bit B. I am encrypting this bit under, I'm generating keys, right? Keygen. I'm encrypting this bit B, give it to the adversary together with the public key. And he gives me back a guess B prime. And I say that when if B prime equals B, right? And we require that no PPT adversary, no computationally bounded adversary A has a winning probability substantially better than 1/2. Okay. But now the really interesting property. So in CPA security is really the same as for standard PKE, nothing new here. The interesting property, one of the two interesting properties of homomorphic encryption is homomorphic correctness. So I require that it holds for all pairs of public and secret keys that are valid outputs of the key generation algorithm, all ciphertexts C1 to Cn that are also validly generated ciphertexts under PK, and all circuits C that if I first run this evaluation algorithm, eval, using public key PK, circuit C and ciphertext C1 to Cn, if I first run this and then decrypt it, this is the same as if I would first decrypt all these ciphertexts, C1 to Cn, and then evaluate this circuit. In a way, it means that, or what the homomorphic correctness property means is that decryption is sort of a homomorphism for all circuits C. So really, I can either first evaluate the circuit C and then decrypt, or first decrypt and then evaluate this circuit. So that's what we mean with homomorphic correctness, that decryption is homomorphic. The second requirement is that we have something called compactness. That is, when I do such a homomorphic computation using the eval algorithm, the size of the homomorphically computed ciphertext does not depend on this circuit C. Why do I have to require this? Any ideas why I need to make this requirement of compactness to make this notion of homomorphic encryption or fully homomorphic encryption in some sense non-trivial? Okay, I'm going to tell you. The reason is I could just have a sort of trivial homomorphic encryption scheme where just the structure of ciphertexts change. I could just define eval, I'm going to leave the public key away, of C, and let's say C1 to Cn is just something that's written as, or now, circuit C together with the ciphertext C1 to Cn. So what I would do is, instead of actually performing this computation, I would take these ciphertexts C1 to Cn and say, okay, this is a computation, please perform it once you decrypt it, right? That's my new ciphertext. So this ciphertext has changed its format. And of course, now it clearly depends on the size of C. I need to include the entire computation into this ciphertext, right? And then decrypting such a ciphertext here, C, C1 to Cn, would now just be, well, first decrypt all of them, C1 until the Cn, and then perform the computation C, right? That looks like cheating, and it is cheating, right? Because I haven't really performed this computation on the ciphertexts. I have just added a computation instruction to these ciphertexts, right? That's why I need to have a property like this compactness in order to make this notion of homomorphic encryption non-trivial, right? So, but in order to forbid this simple cheating here, I have to make such a requirement. Are there any questions? Well, if not, let's first look into a quick teaser. What's the connection of homomorphic encryption, or this encrypted computation, with obfuscation, right? I'm going to tell you quite a few things about how to build homomorphic encryption schemes today, but to sort of keep you interested in the subject matter, let's first discuss how this is related to obfuscation. So normally, a circuit C describes some computation which we want to perform on inputs X. I have circuit C, now they come input X, and the circuit C describes the computation that I have to perform on these inputs X. Now, universal circuits, which I presume you have heard about universal Turing machines in your undergrad education. Universal circuits are the same just for circuits. So for universal circuits, they get both an encoding of a circuit of a computation C and an input X, and they are required to simulate this the computation of this circuit C on X. So think of it this way: a universal circuit U gets two inputs, X and C. I'm writing X into the subscript and C as the explicit input. And think of it this way: I can kind of hardwire X into this universal circuit, and then it just gets as input some other circuit C and evaluates C on X. That's what a universal circuit does. It takes a description of a circuit and evaluates it on X. Right? And here, this is nothing outlandish. Programmable circuits exist all over the place, or FPGAs, right? You can take some circuit which you can program to do any computation of a certain size. Right? Now, of course, a universal circuit is a circuit itself, so it cannot simulate an arbitrarily large circuit, but what you can do is simulate smaller circuits up to a certain size. And for any circuit, or for any circuit size, you will find a slightly larger universal circuit that is able to simulate this circuit, or simulate the computation of this circuit. Okay, and really the connection with obfuscation is on a very high level the following. So if I have a circuit C and I want to obfuscate it, I encrypt this circuit C under an FHE scheme and I get EncC. So now I have an encryption of this circuit. To evaluate this obfuscated program on some input X, what I'm going to do is I will homomorphically evaluate UX on this encrypted circuit C. That is, I'm going to compute eval of UX on this ciphertext EncC, and by homomorphic correctness, this will result in a ciphertext which essentially encrypts UX of C, but now by the property of my universal circuit, this UX of C is just C of X. So what I can do with such an encrypted circuit is I can choose whatever input X I want and produce an encryption of C of X. And now, due to this compactness requirement, this C of X, this EncC of X doesn't depend on the size of C, right? It's basically an encryption of the output, but not an encryption of the entire computation. The challenge now is how, given such a ciphertext, EncC of X, how can we release C of X from this? Or how can we enable the evaluator to recover C of X without releasing additional information about C? I mean, this has to do, or the tools that I'm going to show today will be insufficient to achieve this, but this is the high-level strategy on how we will construct obfuscation schemes. So we perform a computation under the hood. We perform an encrypted computation. The result of this computation will be something small and compact. And therefore, we can hope that this small ciphertext does not leak or will not leak too much information about the circuit C. And then we need to craft a mechanism which allows us to recover this C of X from this ciphertext. Now, of course, I could do that if I gave you the secret key, right? If I somewhere included the secret key along in this obfuscation, but that would clearly defeat the purpose of my obfuscation, because I could just decrypt this EncC and recover C. So I need to do something that's below encryption, but still allows me to decrypt computation results. That's the challenge, right? But today, we'll first look at this notion of homomorphic encryption, of this first part, right? This second, more challenging part on how to recover C of X from this ciphertext. That's what now most of the obfuscation literature is concerned with. But before we can do that, we first kind of have to develop some understanding of homomorphic encryption. As a first example of a homomorphic encryption scheme that probably most of you have seen already is the El-Gamal encryption scheme. Now, El-Gamal, I'm not gonna go through that in a lot of detail, but recall we're working over a cryptographic group G with a generator G. My public key is such a pair GH, and the secret key is the discrete logarithm of H to the basis G. To encrypt, I just choose a random R, compute this G to the R and H to the R times G to the M. So I'm including this G to the R in the ciphertext, and I'm using H to the R to blind G to the M. Now, to decrypt a ciphertext, I just compute, given the ciphertext VW, I just compute W times V to the minus X, right? And if I plug that in, if I have V equals G to the R, W equals H to the R times G to the M, then W times V to the minus X is just H to the R times G to the M times G to the R to the X. But we know, that was one too fast. G to the, I can just switch X and R here. Now, and I get that this is the same, sorry, to the minus X. This is H to the minus R, and I see that H to the R cancels out, and I'm just left with G to the M. And if M comes from a small enough space, if it's like bits, I can just do an exhaustive search to find what M is given this G to the M. That's decryption, but now the interesting aspect is homomorphic evaluation. Now, if I'm given two ciphertexts, C1, just G to the R1, H to the R1, it's in the exponent, times G to the M1, and a second ciphertext, G2, I can perform a homomorphic addition of M1 and M2 by just multiplying these two ciphertexts component-wise. So I multiply these two first parts, G to the R1 and G to the R2, and also the second part. Now, since I'm in a group, I'm having G to the R1 plus R2 and H to the R1 plus R2. And if I call R3 as R1 plus R2, and then I'm having G to the R3 and H to the R3, and that's, sorry, this should be M1 plus M2. Then I'm having, again, a well-formed ciphertext. So I can do homomorphic additions for El-Gamal. I can add encrypted values, given that the values don't grow too much, because, as I just said, for decryption, I actually have to compute a discrete logarithm of G to the M. I can only do that efficiently if M is small. So if the homomorphically computed the homomorphically computed value that's encrypted is too big, then decryption will take too long. So this is at addition. But what about multiplications, right? So additively in some sense, additively homomorphic encryption in this weak form, as in the El-Gamal crypto system, and then later properly, where you can also encrypt and add large values in the Payet crypto system, that was known since the 80s and 90s. But what about multiplications? So it is known, or you probably all know, that additions alone don't allow me to express general purpose computations. If I can just do additions, I don't have the full power, the full power of Turing complete computations, but I do if I have additions and multiplications. So if I can do additions and multiplications, I can compute, I can do arbitrary computations. Essentially, I can run, I can simulate any Boolean circuits. So addition and multiplication together are like as complete as a NAND gate is, right? We know that the NAND gate is just a single gate that allows us to express all conceivable computations. Okay, so this was open for quite a while until 2009, when the first fully homomorphic, or the first candidate of a fully homomorphic encryption scheme was proposed. But we're taking a small leap over that into the year 2013, when a really conceptually simple, as the title says, and in my opinion, beautiful homomorphic encryption scheme was proposed that solves this problem of getting multiplicative homomorphism in a really beautiful way. Okay. Before we dive into this, we have to take a really abridged crash course on lattice-based cryptography. I'm trying to strip that off all the technical details as much as possible. So lattice-based crypto can be quite technical, but what I'm trying in the following hour-ish is to really condense this on a very small number of crucial concepts. So the details can be quite confusing, but what I'm trying now is to convey the essence of what makes up lattice-based cryptography. And I'm trying to stay so abstract that I'm not gonna even mention what lattices are. Okay, so in what follows, Q will be a large integer. Think of something that's, for now, exponentially large, and Q could be a prime number, it could be a composite number, it could be a power of 2, it could be anything. All I need of this integer is that it's sufficiently large, right? It doesn't need to be hard to factor Q or anything. I don't make any such assumptions. So what I'm interesting how this converted my keynote into PowerPoint. This doesn't look as nice anymore. So ZQ will be the ring of integers modulo Q. This is something we're familiar with, happens all over the place in crypto. Like if we take abelian groups, we know they are isomorphic to some ZP for a prime number P, right? If we have a cryptographic group, typically they're just prime order groups for some large prime order P. But now we just have this ring of integers modulo Q. This is, of course, an additive group. We can do additions there, but we can also multiply elements, right? That's the difference here. We have a ring, so we have an efficient way of multiplying ZQ elements, whereas so far we've just talked about basically a single group operation, addition, right? The Algamal crypto system is defined over a group, and in a group we have in an abelian group, we have an addition operation, but there's no canonic multiplication operation. And now ZQ, it's not in any cryptographic group or anything. Those are really just the plain integers modulo Q. And what we're going to do is we will work both with vectors and matrices over CQ. All right. And really, the concept that is most essential or most crucial for lattice-based crypto is that of shortness. So in the following, we will just assume that Q is smaller than 2 to the K, and B is a lot smaller than Q. now here on the right side, I've already drawn a circle, and this is sort of one way to visualize CQ is here I'm having 0 in this clock, here I'm having 1, there I'm having 2, and so forth. At some point I'm at Q half, I'm going further, then I'm at Q minus 2. I'm getting to Q minus 1. And now once I reach Q, this is of course the same as 0, right? Q modulo Q is 0, then I'm back at 0. So I can imagine ZQ to be some kind of circle, right? Where I can sort of just wander around. And addition is really simple. If I get two numbers that correspond, so one number x here and one number y here, I just have to sort of add these two circles, and I'm here at x plus y. Sorry, I'm adding up these arcs. I'm at x plus y. Multiplication is somewhat harder to visualize here, so I'm not gonna go into this. But okay, what I'm interested in now will be no, that was not. What I'm gonna be interested now is some notion of shortness. So in ZQ, I'm having the circle. Whenever I'm hitting this modulus Q, I'm back to 0, right? Then I went a full circle and I'm starting back from 0. But now what I'm gonna do is I'm gonna have a different perspective on ZQ elements. Namely, what I'm gonna do is I'm gonna lift them into the integers, right? And there I'm saying that if this is B and this is essentially minus B, and minus B is the same as Q minus B, right? If I'm in this interval, then I say any number in this interval is short. So how I'm doing this in a way is I'm interpreting everything between 0 and B in ZQ as 0 and B in the ordinary integers, and everything in between Q minus B and Q, which is the same as 0, I just interpret as the interval minus B to 0. So everything that's up here, all these guys that are in here in this interval on this circle, I'm gonna call them B short, right? So really the idea is to just take these mod Q elements and lift them into the integers. Just think of them as an integer for a moment and then take the absolute value. So once I do this and once this absolute value is smaller than B, then I'm gonna call such a number B short. That's a really central notion. So even though I'm working with modular reductions, I am defining this notion of shortness on these modular integers. And a first thing to note here is that if I choose a uniformly random element from ZQ, then it will be in this interval here in minus BB with probability 2B divided by Q. So really only with a very small probability, if Q is a lot larger than B, then such a random element will only be short with very small probability. So most elements in ZQ will be long, and only a small fraction of them are short, right? Now, of course, I can't draw this interval minus b to be super tiny, because then you wouldn't see anything in this picture. But think of this as really just a tiny arc segment. All right. So this was shortness for single elements. Now we generalize this notion to vectors. Now, if you give me a vector x, which is x1 to xn, I say this vector is short if all components xi, I want to say it is b short, if all components xi are b short. A natural generalization, right? A vector is short if all its components are short. And I'm going to do the same for matrices. So if you give me a matrix M, which has components, let's say M is Mij, then this is B short if Mij is smaller than B for all ij. Okay, but now there's the following observation. Give me two vectors x and y that are b short, then the vector x plus y is 2b short, right? If I add two components, I know that each of these components is smaller than b. Well, what do I know about the sum of them? It has to be smaller than 2b. We can do something similar for inner products of vectors. If I know x and y are b short, well, then multiplying two components is b square short. And then taking a sum of n of them will be n times b square short. So, and the same generalizes to matrices. Give me two matrices that are b short, multiply them, you will also get something that is n times b square short. So the bottom line of this is, if b is sufficiently smaller than q, then b short values or vectors or matrices behave just like integers without this mod q reduction. So even though there is a mod q reduction looming somewhere, if we're confined to such a sufficiently small interval around 0, then arithmetic operations will basically leave values that we can interpret as integers still as integers, right? But an important caveat here is, of course, that this bound b grows with every arithmetic operation, right? So in a way, if we start with very short values x and y, and then do a few computations, we will get a looser and looser bound. And at some point, when this, let's maybe go back, when this bound hits, so here we have, so here we have q over 4, and then we have 3 quarters q. When this bound hits q over 4, this notion of shortness starts to become meaningless. So whatever we will do, right, it's definitely meaningless once it's q half, because then it's the entire thing of CQ. So whatever we do, we will, when we do these computations, we will have to start with a pretty small b and just control the growth of this b. In other words, for a given target b that we want to be able to deal with, we have to choose Q sufficiently larger. Okay, so that was this notion of smallness. Basically, small values or short values, even though they are ZQ elements, just behave like integers without modular reduction. That's the bottom line. So even though modular reduction would happen somewhere, we don't feel it, or we don't see it, because we're computing on short values. Okay, now this is really the main concept around which lattice-based crypto is constructed around. But now I will show you a very simple technique which allows you to take vectors that are not short and turn them into short vectors. The way I'm doing this is via binary decompositions. So in the beginning, I said, let's assume Q is smaller than 2 to the K for some K. Since this is the case, we can write every X in ZQ as just some xi 2 to the I, where I goes from 0 to K minus 1. This is really just the binary decomposition of this integer X, right? I know if X is in ZQ, then it is smaller than I can represent it as an integer smaller than Q, and therefore any integer smaller than Q, which is smaller than 2 to the K, can be written in its binary representation, right? So I have these some 2 to the I xi, where all xi are just bits, 0 or 1. It's a standard binary decomposition. Now I'm just going to rewrite this. Right now I've written X in its binary expansion. Now I'm going to define this vector G, which just consists of powers of 2 from 1, which is 2 to the 0, to 2 to the K minus 1. I call this vector G. And with the above observation that every value X in ZQ has such a binary decomposition, I can conclude that there exists a vector in 0, 1 to the K, namely consisting of the bits x1 to xk, such that X can be written as the inner product of this vector G and this vector X, right? So computing this inner product just unrolls this binary decomposition of X. So I've taken a single, in some sense, I've taken a single ZQ value X and expanded it into this vector bold X, which is just the bits of the binary decomposition. And the really the important thing for us here will be that reconstructing the value X from its binary decomposition is just an inner product. That's just the computation of an inner product. It's a linear operation. And now let's observe that this vector X is in fact 1 short, since X is in 0, 1. So every component of this vector is, or let's call it 2 short, right? Because I said strictly smaller than B, then it is 2 short. But we have we can turn an arbitrary ZQ value X into, we can represent it by a very short vector. Or a vector where the components are very short. And now let's slightly generalize this. We can generalize this now that we've done it for scalars, we can also do it for vectors and matrices. So what we have is there exists a matrix G, and this matrix G, I'm not going to write it down. You can maybe try to construct it yourself. It of course is built from this vector G that contains these powers of 2. So that's a matrix which is almost everywhere 0, and but then sort of on the diagonal, on the semi-diagonals, it contains these powers of 2. It's not hard to construct this, but in this fashion, I can construct a matrix G in ZQ to the n times k times n, such that for every x in ZQ to the n, so every vector x, there exists a slightly longer vector x prime in 0, 1 to the k times n. So this vector is longer by a factor k, but it just consists of bits. So this x prime is a too short vector such that I can write x as g times x prime. So turning the binary decomposition of this x prime of this vector back into x itself is just a multiplication with this fixed public matrix G. And in abuse of notation, I will just write x prime, which is the binary decomposition vector, as G inverse of x. Mind you that this G inverse is not multiplying with the inverse matrix of G. That's why I'm writing this with these parentheses. So this G inverse of x is just computing a sort of the binary decomposition with respect to G of this vector x. And now, of course, PowerPoint has done a line break. Now what I get is that G times G inverse of x is x. Right? So even though this G inverse function is nonlinear, if I apply the linear operation G to G inverse of x, then I get back x. So you can think of applying the linear operation G on the left side is a left inverse operation of this G inverse of x. And likewise, I can do the same for any matrix M in ZQ to the n times m. So there exists a matrix M prime, which now has just a certain number more rows, or a factor k more rows. It has now n times k rows, such that M can be written as G times M prime. And again, I will also write M prime as G inverse of M. And we have that G times G inverse of M equals M. And really, there's no magic happening here. This is just binary decompositions, right? This is really just observing that reconstructing binary decompositions is a linear, or going from binary decomposition to the standard representation of a ZQ number is just a linear operation. And really the takeaway here is that this G inverse operation turns vectors or matrices into two short vectors, but with a larger dimension. That is, if you're starting with a vector of length n, that's anything in ZQ to the n that's sort of really dense, then we kind of, what this G inverse does is we're spreading out this mass into a short vector, right? So this new vector will have a larger dimension. It will be longer, but in the notion of this shortness that I've defined earlier, this will be a short vector because every component of this vector is short. Are there any questions? If not, let's continue. Now I'm just dropping two things in front of you without any proof because, well, we don't have time for this. This is in a way standard stuff, but I'm just encapsulating this like on two slides now. The first thing is the leftover hash lemma. If you will see, if you think of this, this will be something quite intuitive. Let's say we choose a uniformly random matrix from ZQ to the n times 2kn, and this constant 2 is somewhat arbitrary. Really, the second part could be anything sufficiently larger than k times n, right? It's k times n plus something, but really for sake of simplicity, I just chose 2 times k times n. So with these parameters, everything works nicely for sake of concreteness, but that's not the tightest possible parameter we can choose here. So D is a dense, uniformly random matrix chosen from the entire domain, from ZQ to the n times 2kn. And now I'm choosing a random binary matrix R from 0, 1 to the 2kn times m. So these two matrices, the number of columns of D and the number of rows of R match. So what can we do with them? Well, we can multiply them. And what the leftover hash lemma says is that I give you D and D times R, then this is statistically close, essentially looks like for any even unbounded distinguishing process, or for any unbounded distinguisher as well, still D. But now instead of D times R, I am having a uniformly random matrix U. So really, the right way to think about this is the technical notion. The right way to think about this is that when I first choose a uniformly random matrix D and multiply it with a short random matrix R, then this gives me a fresh uniform matrix U. Right? This D times R is really, for all practical purposes, a uniform random matrix U, and in fact independent of D, right? On the right side, D and U are chosen independent. So even though I computed this U or D times R from D, by this multiplication with this short R, it looks like just a new, fresh, random matrix U. So in this process, really the important thing is that when I compute this D times R, then R is consumed. I can only use R once to compute such a U, but D is not consumed. So I can do this over and over again with the same random D, right? I could do this many times and D would not be consumed. Think of D as a catalyst of sorts, which when multiplied with these matrices R that are only random on on the set of short matrices, on binary matrices, then this gives us a dense matrix which is really close to uniform. The name leftover hash lemma is a little bit, so this is just a special variant of the leftover hash lemma. In general, this holds for a much broader class of operations. So here the hash operation is just multiplying an input R with a hash function D. That's the hashing part here, right? And this is a linear hash function, but this leftover hash lemma holds for a much wider class of so-called universal hash functions, which behave similar to multiplying with a random matrix D. But really, that's all we need. Give me such a short random R, multiply it with D, and it looks like a fresh random matrix U. Okay. And now, the only hardness assumption for today, the so-called learning with errors problem, and I present it to you in an extremely abridged way, right? Purists would probably leave the room screaming now, but really for our purpose, this shall be sufficient. So I'm just going to tell you that there is a way of sampling matrices A in ZQ to the n times 2kn together with a vector S in ZQ. Neither of those are short, such that the following three properties hold. The first one is that if I multiply S with this matrix A from the left side, right? So if I have my matrix A here, this 2kn is bigger than n. If I have my vector S here, if I multiply them together, so what I do is I take a linear combination of the rows of A with this vector S. S defines this linear combination of these rows. I will get something short. I will get this vector E, and E will be B short. So what this says is there is a way to combine the rows of the matrix A to obtain something short. And the way to do this is use S as linear combination. Good. So now we meet again our friend, the notion of shortness. The second one is, I mean, seems kind of weird at a moment, but we will need that. Is of this vector S, the last component is 1. So my vector S will be something in the first and so forth, something in the n minus first position, and the last component of this vector S is 1. Okay, so those are two technical properties, but now comes the actual assumption, namely the way I've sampled this matrix A is that given A alone, so A without this vector S is computationally indistinguishable from a uniform matrix D. So pretty much the same kind of matrix we've seen on the last slide with the leftover hash lemma. So this matrix A, there is a way to combine its rows such that there is a short vector in its span. But on the other hand, this matrix should computationally, or for any efficient distinguisher, look like a uniform matrix. So I'm saying it should look like a uniform matrix. The first question that can or should maybe go through your head now is, well, would there actually be a way to sample such a matrix A such that A is in fact actually uniform or statistically close to uniform? I mean, the question would come down to asking whether any such matrix A could have a such an S such that S times A is short. And the answer is, well, this indistinguishability can only be computational. So A and D cannot be statistical close. Namely, this vector S, such a vector S, in fact, is a witness of sorts for A not being uniform. So if I don't give you this vector S, everything's fine, right? Then A looks to any computationally bounded process like a uniform matrix. But once I give you this vector S, you're convinced that this matrix A was with very high probability chosen from a distribution that is not uniform. Right? So think of this vector S as a certificate or a witness which kind of demonstrates that A was not chosen uniformly random, right? And really the way to kind of see this, let's say, such an A cannot be statistically close to uniform. Why is that the case? Well, on the one hand side, such an S can be found by brute force search. Brute force search if it exists. That's the first thing. The second thing is now if such an S exists, we know that S times A times R, and this is again in 0, 1 to the n k times m, right? Uniform in uniform in 0, 1 to the n times k times m. This is this is the same as S times A times R, right? But now we know S times A is just E. So we have E times R. Now we have E, this is short, and this is also short, right? And earlier I've said the multiplication of two short things, I'm ignoring the concrete parameters for now, but multiplying two short things will again be short, so this is short. On the other hand, if instead of A times R, I had a uniform matrix U, then S times U is uniform. And as I said in the very beginning, something uniform in ZQ to the M that is now, and that, and therefore not short. Right? So stuff that I choose uniform from the entire domain doesn't end in this narrow small domain of, or in this narrow range of small values with very high probability. But the leftover hash lemma essentially said that A times LHL, AR, and U are stat close, sort of, therefore need to behave similarly. Right? But what we've just seen, they don't behave similarly. So in the case that I've sort of sampled A with a short s, no matter how, then this s times A times R will be short. On the other hand, if on the other hand, if I take a uniform matrix U instead of AR, then for any S, for any non-zero S, S times U cannot be short, or will with high probability not be short. So these two distributions behave very different, right? And what we conclude from that, we can show that differently, but that's just given the tools that I've shown you. A and D are statistically far, or need to be statistically far. Okay. Now, now that we've briefly discussed the LWE problem. So LWE, what we store in our subconsciousness, so to speak, is there's a way to sample ZQ matrices with a short element in their row span, which is something very unusual, which doesn't happen for random matrices. Okay. So now that we've discussed this, we've assembled all the tools to discuss the Gentry-Sahai Waters fully homomorphic encryption scheme. So key generation is very simple. I mean, simple in the abstraction that we talk about it. I generate such a matrix A, as I've just discussed, together with a vector S via the LWE distribution. So this LWE assumption just gives me a mechanism to generate such a matrix A, which looks random, together with this vector S. My public key will be A, and the secret key will be S. That's key generation. I've basically outsourced all the complexity in how the LWE distribution does this. We're not concerned with this. Now let's look at encryption. Encryption takes a public key, which is this matrix A, and a message M, which for now is just a bit. It's 0 or 1, and does the following. So first, it chooses a uniformly random matrix R from 0, 1 to the 2kn times kn. And then it computes a matrix C, as C is also a matrix, as A times R plus M. Recall, this is just a bit, plus M times G. G is this matrix I defined earlier when I talked about binary decompositions. Right? This is maybe a bit, right? Why do it like this? Right? But we'll see that there is some magic to this. But in technical terms, it's kind of something simple, right? We have this matrix A, which specifies the public key. We choose this random binary matrix R, we multiply A with R, A times R, and then we just add the message times this matrix G, right? So we sort of encode the message M by multiplying it with this public matrix G, and then we blind it with A times R. Okay, keygen encryption. Now, typically it's time to discuss decryption, but let's make a short intermezzo and prove in CPA security of this scheme inline. So really proving security is in a way the most simple aspect about this scheme, given the tools that we've seen so far. So my adversary, really, I really keep it short, view of adversary, he basically gets the public key and this C equal enc pk of the bit B, right? And the public key is just this matrix A. And the encryption of the bit B is just A times R plus M. I just called it B. B times G. Okay. So the first thing that I'm doing is I'm observing, wait, so A comes from this LWE distribution. So A is from LWE distribution, but I don't see this S being used anywhere. And I know when this S is not floating around, when the secret key is not floating around, A looks like a uniformly random matrix D. So under the LWE assumption, this looks like D comma D times R plus B times G. Okay, now this D here is uniformly random. Great. So now I have a uniformly random matrix D, and I have D times R. Well, we've just discussed the leftover hash lemma, right? If D is uniformly random, then I have D comma U plus B times G, where this is now also uniformly random, and independent of D. Nice. Okay, so I have D comma U plus B times G, but this U doesn't appear anywhere else. So essentially this U plus B times G, since U is uniformly random, that's essentially a one-time path. Shifting a uniformly random or shifting any value B times G, whatever that was, by something uniformly random is now, in fact, identically distributed. This is identical to D comma U prime, where this is also uniform. Right, but via this transformation, I've transformed a view of an adversary that depends on this bit B that he has to guess into one that is independent of B. Dependent of the bit B. Therefore, in this transformed experiment, the adversary's probability of guessing B are exactly 1/2. So I've only done computationally indistinguishable steps, right? The adversary can't tell each of these transformed experiments apart from one another. And in the last experiment, his winning probability is exactly 1/2. That means his original winning probability can be more than negligibly better than 1/2. And therefore, well, we conclude that this scheme is INCPA secure. Come on, next slide. So decryption. Decryption, we still have a little, I guess, I would run over time. So let's just discuss decryption and then next time finish up with the actual magic of that scheme with how homomorphism works. So let's say we have dec sk of a ciphertext C. Let's see how this works. Our ciphertext C is of the form A times R plus M times G. And what I can do now, well, I have this A times R. We've earlier seen when I discussed the LWE problem that, well, something interesting happens when I multiply A with this vector S, right? Sk is S from the left side. So what happens here? S times C, the ciphertext C, is just S times A times R plus, well, S times M times G. But we know that this S times E is a short vector E. And now we know that R is also short. So this is short. That is short. And M is just a bit, right? It's therefore just a scalar. So it can switch places with S. So this is no, plus M times S times G. And now, okay, what can I do with this? Well, I have this M times S times G plus something short, right? This entire thing here is short. So now I'm doing sort of something that seems magical maybe, and that's where the magic happens. I'm just defining a vector V. Let V equals just a vector which is all zeros, and in the last position it's q over 2, right? And this is in the q to the n. So there's a vector of length n, 0 everywhere, but in the last position it's q half. All right. And now instead of just computing S times C, do I have? Yes. Instead of just computing S times Z, I'm computing the following value, a value Z, which is S times C times G inverse of V, right? I've computed, I know already what S times C is. That's just, well, E times R. Now I need to multiply it with G inverse of V plus M times S times G inverse of V. This is now where the magic of sorts will happen. Even though I've used completely muggle ingredients, right, to build this scheme. So I know that E times R is short. I know that G inverse of V is short. That's that was the entire purpose of this binary decomposition, to make it such a G inverse of any vector, and therefore G inverse of V is as well is short. Therefore, this part here is short. Right? On the other hand, G times G inverse of V, that's just V. This is equals V. So I'm having what this part here is, that's just M times inner product of S comma V. But now let's look at this vector V. This is just 0 everywhere, right? If we look at this, this is 0 everywhere and Q half in the last position. Now, remember earlier when I defined the LWE problem, I said that the last component of S is 1, right? And now I have Sn equals 1. Therefore, this inner product is just 0 times whatever goes on before plus 1 times Q half. So, come on. So this thing, this inner product is just Q half. So I'm having M times Q half. So altogether, I have that this, wrapping this up, S times C times G inverse of V, I'm reordering it, is Q half times M plus, let's call that E prime. Let's call this thing E prime plus E prime. And this E prime is short. So let's go back to our representation of ZQ as a circle. And I've said, it's not a nice circle. I've said that M is a bit either 0 or 1. So if M equals 0, well, then we know that this value Z is just of the form E prime, and E prime is short. So we know that this value Z for the case M equals 0 lives in this interval. On the other hand, if M equals 1, then we're of the form Q half. Q half plus E prime. So here we have Q half, here we have 0. Then we're down here, we're in, then our value Z is there. So what can we do now? Well, we know that if the message M is 0, then we get something close to 0. If the message M is 1, we get something close to Q half. So really all that decryption has to do is check if Z is closer to 0 or Q half. In the first case, we decrypt to 0, and in the second case, we decrypt to 1. Great. So this is how decryption works. Now, I guess we still have 6 minutes time. So let's briefly talk about additive homomorphism. Now, really, the magic is multiplicative homomorphism, and I'll have to postpone it until next time. But additive homomorphism is really simple. In fact, it works pretty much in the same way as additive homomorphism for the El-Gamal crypto system work. So we have two ciphertexts. C1, let's say this is A times R1 plus M1 times G, and C2, which is A times R2 plus M2 times G. And I'm just defining eval of, well, public key I won't even need, but of this plus operation of C1 and C2, this homomorphic plus operation, I will just define it as C1 plus C2. So to homomorphically add the plaintexts, I'm just gonna add these two ciphertext matrices, right? And by writing things out, you will see that C1 plus C2, if you write that out, this is just rephrasing this, A times R1 plus R2, or I can write this as A times R1 plus R2 times M1 plus M2 times R. And I'm just going to call that thing here R3, right? So I have A times R3 plus M1 plus M2 times R. So this looks like a valid encryption of M1 plus M2. The only thing is now that if R1 and R2 are B short, and if they're fresh encryptions, we know that they're too short, then R3 equals R1 plus R2 is 2B short, right? So if we started with something that's really short, and when we freshly encrypt, it will be very short, then we get an R3, which is still sufficiently short. And otherwise, this is really just the same, or the same thing is happening as in El-Gamal. We really just added these ciphertexts together and get an encryption of M1 plus M2, right? And decryption works as long as R3 is sufficiently short, right? We've established that if R1 and R2 were pretty short, then R3 is still sufficiently short, and therefore, come on, decryption still works. Okay, that's not yet the magic. The magic happens with multiplicative homomorphism, but now I've run out of time, so let's just take 15 minutes from the next lecture and see how this magic of that scheme comes all together. Okay, so since we're out of time, I'm gonna finish this up here.
I would have one question.
Yes, please.
If concerning the additive homomorphism, if we add M1 and M2, isn't it? Don't we need like a 4-quarter range later on? Like if they're both 0, then we're at 0. But
yes,
if they're both 1, for example, we'd be at 2. So
yes. So we will also have to. I mean, that's why I said we're working with messages that are from 0, 1. Right, so when we do additions, the message will grow. But if you look into the decryption operation, right, the decryption essentially, can only return 0 or 1, and what you get as the output is the encrypted message modulo 2. So when we add ciphertexts, this corresponds to an addition modulo 2 on the plain texts.
Okay, that makes sense then.
This will correspond. Let's maybe add that here. Addition or homomorphic correctness for addition. Let's maybe homomorphic correctness. Homomorphic correctness for addition modulo 2. Great, thanks for the question. Okay, I think I will, unless there's another question that we should include in the video, I'm gonna stop the recording now.
I think, one second, I think on this slide in the line where you have C1 plus C2, in the end it should be G, not R.
Oh, thank you. Thanks, good, great, thanks a lot. That is correct. Awesome. Okay, anything else we need to? Okay, so I think I will stop the recording now.